Hello and welcome to the lecture number 20 of Physics 401A. In the last lecture, we discussed the application of regular perturbation theory in the case of a weakly perturbed equation of a simple harmonic oscillator where the perturbed term represents a very weak damping term. Okay, and we already showed that the application of regular perturbation theory is not a very appropriate one because it gives the birth of term called the secular term, which grows linearly with time. Okay, or which, I mean, in general, which grows linearly with the independent variable x for according to our last lecture. Okay, now the question is that whether this type of solution is logical or physical or not. Well, we said that if the independent variable is considered to vary within a small range of, within a finite range of small or moderate values, so that the total term the total secular term always can be considered as a perturbative contribution to the global solution, then we can say that this is okay. Okay, or if we can have some system where we don't do perturbation method, but the system basically as a resonant solution permits this type of secular terms, but where we have enough physical reason to support or to justify the secular term, then it is also okay. For example, if we have an if we have an undamped forced oscillator, okay, where the periodic force which is incumbent on the system, okay, has the same frequency with that of the natural frequency of the system, we know that the system will resonate, and then the resonant solution will give us a secular term, and that's completely logical for that case, because here we can easily understand that the system is continuously receiving energy from the force source. So there is no violation of energy conservation or anything. Okay, you have a continuous source of energy and you are just continuing to grow your the amplitude of your solution, or not even amplitude, but your grow the total value or the magnitude of your solution with time. Okay, so that is something very very important to understand, that whether a secular, just having a secular term in your equation always does not say that this is absurd. Okay, it depends on the condition. For perturbation methods, when we came across the secular term, basically we showed that for a damped oscillator where the damping is very weakly done, then we don't have any reason, so that we have a secular term which grows linearly with time. Okay, but this was just, and we then said that of course that means that the equation, the perturbation method has some problem in it. Okay, so maybe we have to modify the method of perturbation itself. Okay, now this was all about this was the case of a linear ODE, or ordinary differential equation. Okay, where you just make a d2x dt2, or for example d2x dt2 plus some constant times dx dt plus x is equal to 0, and that constant times dx dt term is of the first order of smallness. For example, it's proportional to epsilon. Then we discussed the solution in the last for this type of equation. We discussed the solution in the last lecture, but here we will start discussing a bit different thing, that is, the equation now should be non-linear. Okay, now this type of one class of this type of equations, they are called the Duffing equations. Okay, so basically Duffing equation models an elastic oscillator whose range of activity does not really lie within the so-called proper elastic limit. That means it does not exactly obey Hooke's law when the force incumbent on the spring or the oscillator, okay, does not simply proportional to the to the incremental distance or incremental deformation, okay, but can be depending on the higher order of that deformation as well, okay. So the simplest model of such type of nonlinear oscillator can be perceived from the equation d2x dt2 plus omega 0 square sin x is equal to 0. If you all know that it simply gets reduced to our very well known simple harmonic motions equation, where this is nothing but d2x dt2 plus omega 0 square x, only when we are considering very small x. If x is not small, okay, then of course we cannot just say that sin x is proportional, is almost equal to x, okay. Then we have to take the higher order terms of the expansion of sin x, okay. And you can easily also identify that most of the cases this x is basically replaced by theta, the angle theta, okay. So we say that for very small angular displacements, sin theta will be very close to theta in the limiting sense, and then we will easily solve that system, okay. But if let's say this is not so small and we have to keep up to the terms up to the order of x cube, so in sin x's expansion, the next higher order after x to the 1 is x to the 3, x cube, okay. So then we just write that d2x dt2 plus omega 0 square x minus x cube by 3 is equal to 0, okay. So this is a type of Duffing equation, of course in its simplified form. More formally, so this is the term, this is the equation where we just have inserted the nonlinearity, okay, but no damping, no forcing is there. Now we add a damping proportional to dx dt, and we also add a periodic forcing, okay, which is of the nature of some constant f0 times cos omega t, okay. So omega 0 was the natural frequency of the system, and omega is the frequency of that force, okay, the periodic force. Then the total equation we can write x double dot plus 2 alpha x dot plus omega 0 square x plus beta x is cube. Now that beta is here is omega 0 square by 3 with a negative sign. Of course you can easily understand that omega 0 square and omega 0 square by 3, they are of the same order. So this is not a perturbative case, okay, and that the whole thing is equal to f0 cos omega t, okay. So first of all you understand that there is a nonlinearity, so this is the second order equation, and finally you have a non-homogeneity. That means this whole thing, so x double dot plus some constant x dot plus some constant x plus some constant x cube is not equal to 0. So that those type of equations are known as homogeneous, a non-homogeneous equation, okay. If the right hand side is 0, then we can say this is basically homogeneous equations, okay. So the general form is for this type of equations is given by, again, x double dot plus delta times x dot plus alpha times x plus beta times x cube is equal to f0 cos omega t. Now this term, okay, which comes as a, which comes being multiplied with x cube, okay, this beta x cube which is proportional to x cube is called the Duffing term. That is because George Duffing, for the first time, he he discovered this equation, okay. For the first time he discovered, and also he contributed a lot to analyze the equation. Now Duffing equation is a second order nonlinear ordinary differential equation with a non-homogeneity due to the forcing term, as I just said. There is no general method to solve this equation. That is the first message, okay. So don't take a belief that we can actually solve this equation in its general method analytically. So there is no general method to solve this analytically, first thing. However, analytical solutions may be permitted, okay, if we make certain assumptions. For example, we can use, and that exactly we will do here, use perturbation method if we assume the Duffing term to be small compared to the other terms of the equation. Now that is a reasonable approach, because we know if the Duffing term is not there, then we know, so the unperturbed equation is nothing but an equation of a damped and forced oscillator, and we know how to solve that exactly. So the unperturbed equation we know how to solve exactly, then we can perturb the equation a little bit, okay. But then of course you have to understand that beta need not be, so beta is equal to omega 0 square by 3 is not the correct equation to address by perturbation method. Perturbation method can only be used if this beta is at least one order small. That means beta should be some epsilon times something, okay, some moderate constant. So this has to be kept in mind, okay. So for the sake of simplicity, we first try to solve equation 3, that is your equation 3, but in I mean we should get rid of some constants from there just by choosing suitable unit systems and suitable choice of suitable constants of the system, okay, that we can always do, okay, most usually, okay. Now we first to solve equation 3 without forcing and dissipation. So first we forget about the non-homogeneity part and this dissipation part. So we only have this x double dot plus omega 0 square x plus, now you see we have injected a very small parameter epsilon with this x cube term. So it will be epsilon b beta times x cube, and the whole thing will be equal to 0, okay. And epsilon is such that it ranges between 0, but it is always very smaller than 1, okay. Again here you can see that for simplicity we have made omega 0 and beta is equal to 1, so that the final form which we will attack now will be x double dot plus x plus epsilon x cube is equal to 0. Now we have to, so this is a second order equation, so we need two initial conditions or two boundary conditions, whatever, okay, to solve that. So then let us take x at t is equal to 0 is equal to 1 and x dot at t is equal to 0 is equal to 0. So it starts from rest, okay, but it starts from a point which is equal to 1, where x is equal to 1, okay. Now we blindly apply the so-called regular perturbation method, and we write the whole the global solution as a power series of epsilon, okay, and x0, x1, x2 they will simply be the first order, so zeroth order solution, first order solution, second order solution, this type of thing, okay. And so the global solution will now be x0 plus epsilon times the first order solution plus epsilon squared times the second order solution, like this, okay. So putting all this expression in the original equation 4, this one, okay, in the red box, you can easily write this x0 double dot plus epsilon x1 double dot plus to infinity plus x0 plus epsilon x1 plus dot dot. So this is the part of x, this is the part of x dot, and this is the part of epsilon x to the cube, and now x to the cube will be x0 plus epsilon x1 plus dot dot up to infinity cube. Now here we will just keep the first order term, okay, always, okay. Now of course you can easily understand here there is an epsilon already multiplied, so x0 of here and x0 of here there, they are not of the same order, okay. So now if you just like accumulate, or if you just group the coefficients of different powers of epsilon for zeroth power or zeroth order, you will see that your equation will be x0 double dot plus x0. So x0 double dot will come from here and x0 from here. Here the zeroth order term itself is multiplied with epsilon, so globally it should go with the first order terms, okay. So you have this equation, and that's completely reasonable because you should get back your unperturbed equation, and that's quite okay. So x0 will be now some a cos t plus b sin t, Okay, and x0 dot will be minus a sine t plus b cos t. Right? As simple as that. Now we say that initial condition says x is equal to 1 at t is equal to 0. It simply means that the whole solution is equal to 1. So that means if you just keep the terms up to order 1 of epsilon, you can actually write x0 at 0 plus epsilon times x1 at 0 is equal to 1. So this is 1 is a, zeroth order term. So if for example we can say that the at x is equal to, at t is equal to 0, x will be 1 minus 2 epsilon, then you will have x10 will have a value of minus 2. Okay, here you don't have any other terms associating epsilon or anything, so that's why all the higher order terms, all the higher order solutions for x will vanish at t is equal to 0. At t is equal to 0. Okay. Now then you can say x00 is equal to 1 and x10 is equal to 0. The same thing can be applied over here, and here it is 0. So for all the orders of epsilon, all the powers of epsilon, the coefficients will vanish. Okay, at t is equal to 0. So x0 dot 0 is 0, x1 dot 0 is 0. Okay, I just said that. So initial condition is x is equal to 1. So it simply give us in this equation a is equal to 1. Okay, you understand why? I mean, in the both equations actually. Let me just settle this. Because at t is equal to 0, it is a, and this is 0, and this is 1. So a will be equal to 1. Straightforward. And then you can write x0 is cos t plus b sin t. Then x0 dot at t is equal to 0, this is 0 and this is 1, so b is equal to 0. Okay, so finally your x0 will be simply cos t. Okay, now coefficients of epsilon 1 gives another equation. Okay, and that equation is the first order equation. We say x1 double dot plus x1 plus x0 cube is equal to 0. Now you know x0 in terms of t. So then you can easily substitute the value of x0 in this equation. So this equation is now a second order but non-homogeneous equation. Remember, we did not have any non-homogeneity in the original equation because we already forgot about the forcing, but this non-homogeneity came for the first order solution as the contribution or the presence of the zeroth order term in the first order solution, first order equation. Okay, so you can write minus cos cube t as minus 1 by 4 cos 3t minus 3 by 4 cos t, right? So this is, you can now think of the equivalent system for the x1. Okay, so it will be x1 double dot plus x1 is equal to minus 1 by 4 cos 3t minus 3 by 4 cos t. So which is equivalent to two forcing terms. One is with frequency 3, another is with frequency 1. Now you see the physics is very interesting. That says that the zeroth order solution is acting on the first order solution, or the zeroth order solution basically, or the zeroth order solution, yeah, x0 acts as a forcing term for the first order one. So this is the very basic consideration of a system when we consider, for example, for complex flows, the multi-scale phenomena or something. So the effect of one scale, rather the preceding scale, immediately preceding scale, can be perceived as a forcing or as a source of energy. Okay, that can be as well as a sink of energy. Okay, if it is negative, that is also possible in some cases. But just to generalize, it's a source of energy to the successors or the immediately subsequent scale. Okay, or the following scale. So that part is a very important concept in case of multi-scale phenomena. For example, a turbulent motion. Okay. No, but here coming back to this mathematical problem, now we have to recall the method of finding particular integrals for undamped force vibration. Okay, so like the total solution of x1 will be the solution of the homogeneous equation, that means x1 double dot plus x1 is equal to 0, and will be a particular solution taking all these non-homogeneities. Okay, and now this question comes that we now have this equation, uh, like this equation as in a general form: x1 double dot plus x1 is equal to a cos omega 1 t plus b cos omega 2 t, where a is minus 1 by 4, omega 1 is 3, b is minus 3 by 4, omega 2 is 1. Okay, now you see that this is an equation. If you just concentrate over this part, this is an equation with natural frequency 1, right? Omega 0 squared is 1 for x1. Okay, so this part is also represents a forcing with angular frequency 1. Okay, so this part will resonate with this system, but this part will not. So for this part we will calculate a non-resonating particular integral, which will nothing but be a cos omega 1 t by 1 minus omega 1 square, because omega 1 is not equal to 1 but omega 2 is equal to 1. That's why we can never write this type of equation, but we will have a resonant solution, which is the so-called secular term. Okay, b by 2 t sine omega 2 t. Okay, if you remember the previous lecture. Okay, lecture number 18. Okay, so then you can easily see that how to calculate this non-resonating and resonating particular integrals. Now finally, the total particular integral will be the superposition of the two. So you will finally have 1 by 32. So you just have to substitute the values of omega 1 and a, b and omega 2 over here. And finally you will have 1 by 32 cos 3t minus 3 by 8 t sine t. Okay. But this is not the end. The total solution for x1 is the solution for the homogeneous part, which is the complementary function plus the particular integral. When you write the whole solution, then only you can find a1, b1, etc. using the initial conditions, not before that. And you can of course differentiating once, you can have x1 dot, which is nothing but here minus a1 sine t plus b1 cos t plus 3 by 32 minus sine 3t minus 3 by 8 sine t. Okay, so initial conditions again give a1 is equal to minus 1 by 32. Now we can use initial conditions. Please check that. That is your task. I am leaving it for you. And b1 is equal to 0. This is very easy. Okay. So the final expression for x1 is nothing but x1t is equal to minus 1 by 32 cos t plus 1 by 32 cos 3t minus 3 by 8 t sine t. Okay. Now a very interesting exercise will be to redo the whole calculation starting from the beginning without assuming omega 0 is equal to 1, just keeping omega 0 there. Okay, that you can do. Okay, now that was the complete solution for x1, but what about the complete solution for x up to first order? You will see that will be nothing but x0 plus epsilon times x1. Don't forget, epsilon is multiplied with x1 in the global solution. So x1, x of t will now be the 0th order solution cos t plus epsilon times minus 1 by 32 cos t plus 1 by 32 cos 3t minus 3 by 8 t sine t plus higher order terms. Okay. Again, t tends to infinity simply implies that xt also is tending to infinity. And that is because of this term, the secular term. Okay. Now the question is whether it is okay or not. Okay. For that, we have a very elegant method, and we can actually show this is not okay for Duffing equation. So when we come across a secular term as a resonance solution of an undamped force oscillator, we were not surprised because the system has a continuous source of energy through the periodic forcing system. But we also have encountered a secular term in the perturbative solution of an unforced Duffing oscillator that we just have done. Okay, and this is not physical, because there is no source of energy, and we can actually show that much more directly from here. Okay, and that will be shown by this: x double dot plus x is equal plus epsilon x cube is equal to 0, and then you can just multiply x dot throughout, and you will have ddt of half x dot square plus ddt of half x square, these two terms. Okay, and this term you can write epsilon by 4 ddt of x to the 4. So finally ddt of this whole thing, half x dot square plus half x square plus epsilon by 4x to the 4 is equal to 0. So this is a constant quantity. Now you see that all of them are positive definite. Epsilon is also positive. Okay, we all know by definition. So all this is the sum of three positive definite quantities. So just if you take x square, for example, that will be smaller than the whole thing. Okay, so if you just use the initial conditions now, you can easily check that this constant will be simply equal to half plus epsilon by 4. You understand, right? Because at t is equal to 0, x dot is equal to 0, and x is 1, and so you can simply have the constant will be equal to half plus epsilon by 4. So your x square will always be less than, strictly less than, okay, because x square will be there and x4 is also there. These two terms are there. So x square will be less than 1 plus epsilon by 2. Okay, and then x will be bounded by root over 1 plus epsilon by 2, which is again bounded by, so epsilon is greater than, very small, smaller than 1. Okay, so actually that will be even very small, but well, since there is an square root, I just wrote this smaller sign. So root over 3 by 2. Okay, so actually the value of x should be much smaller than 3 by 2. You will think that. Okay, but in any case this is finite. So similarly we can show that x dot is also less than root over 1 plus epsilon by 2, and that's the same thing for the minus x as well. So that means, and minus x dot as well, because there we have just put our conditions as the squares. Okay, so it's all about the modulus values. Okay, so this means that the solutions xt and x dot t, they are bounded. It means the perturbative solution containing the secular term cannot be a realistic solution. So what is the conclusion? Like we did for the weakly perturbed damped oscillator as well, that the regular perturbation theory is not a good choice for our case. So let us search for an alternative method of perturbation. So this is not a good choice. Okay, and a very good recourse for that is the Poincaré-Lindstedt method, which we will be learning in the next part. Okay, and this basically says that we can, by moderating the perturbation method a bit, we can get rid of the secular term. Okay, and in addition we have a global periodic solution for the perturbed equation, and that is something very interesting which we will do. Okay, now here I just stop this lecture. So in the following part we will discuss about the Poincaré-Lindstedt method. Okay, thank you.